Okay, so yeah, we're going to do our final session in the model selection chapter, and we're going to look at ridge regression and lasso. And once again, we're using our R Markdown in R Studio that will help us create a nice document at the end of the session. And it's, as we've seen, it's just as simple as having a script, but it's better because you get nice annotation at the end of the day. So let's have a look at the screen and see our heading. We've got ridge regression and the lasso. And for this, we're going to use the package GlimNet. GlimNet's a package that I actually manage on CRAN, and it's been created by myself, Jerome Friedman, and Rob Tibshirani for fitting lasso models, ridge models, and a whole class of models in between, elastic net, which we won't cover in this class, and for a lot of different loss functions, so we can do logistic regressions, ordinary regressions, and a variety of other models. We'll be using ordinary regression yet. Yeah. So we'll run library GlimNet, and GlimNet doesn't use a formula language, so we're required to give it a matrix X of predictors and a response vector in this case. So we create those by using methods by which by this time we know how. So we make an X and a Y, which is the predictor matrix and the response. And we'll first fit a ridge regression model. So GlimNet's got an alpha argument, and alpha equals 1 is lasso, and alpha equals 0 is ridge. And if you look on the help file, you'll see instructions on how to, on some of the other arguments. And for alphas in between 0 and 1, you get what's called elastic net models, which are in between ridge and lasso. But for us now, we'll just focus on alpha equals 0, which is ridge. And so we do that, and it comes back very quickly. GlimNet's extremely fast, and this isn't a big data set, so it's especially fast. Let's use a plot method for a GlimNet object. And this is kind of interesting. It makes a plot as a function of log of lambda. And what it's plotting are the coefficients. So if you go back to the lectures on ridge regression and lasso, you'll see that the models are penalized ridge regression's penalized by the sum of squares of the coefficients. So penalties put on the sum of squares of the coefficients, and that's controlled by a parameter lambda. So the criterion for ridge regression is residual sum of squares, which is the usual for linear regression, plus lambda times the summation j equals 1 to p of beta j squared. So it's trying to minimize the residual sum of squares, but it's been modified by a penalty on the sum of squares of the coefficients. So if lambda is big, you're going to want the sum of squares of the coefficients to be small. So that'll shrink the coefficients towards 0. And as lambda gets very big, the coefficients will all be 0. And so what GlimNet does is it actually develops a whole path of models on a grid of values of lambda, quite a fine grid, about 100 values of lambda. And so we see here on the log scale, when log of lambda is 12, all the coefficients are essentially 0. Then as we relax lambda, the coefficients grow away from 0 in a nice smooth way, and they get, the sum of squares of the coefficients is getting bigger and bigger until we reach a point where lambda is effectively 0 and the coefficients are unregularized. And so these would be the coefficients that you get from an ordinary least squares fit of these variables. So GlimNet will create the whole path of variables. So unlike subset and forward stepwise regression, which controls the complexity of a model by restricting the number of variables, ridge regression keeps all the variables in and shrinks the coefficients towards 0. Okay? So it gives the whole path. We need to pick a value along the path, and GlimNet's got a built-in function called cv.glimnet that'll do cross-validation for you, k-fold cross-validation. And so we'll run cv.ridge. It's done by default 10-fold cross-validation, and then we can do a plot. There's a plot method for that. And it gives you a nice plot of the cross-validated mean squared error. And there it goes, and you see it dips down. In the beginning, the mean squared error is very high. The coefficients are restricted to be too small. And then at some point, it kind of levels off. This seems to indicate that the full model is doing a good job. There's two vertical lines. The one is at the minimum, and the other vertical line is at one standard error of the minimum, within one standard error. So it's a slightly more restricted model that does almost as well as the minimum, and sometimes we'll go for that. And at the top here, it's indicating that at all stages, there's all 20 variables in the model. So that's our 19 variables plus the intercept. So that's ridge regression using GLIMnet. Let's use a lasso model. Now, if you recall, the lasso was similar to ridge regression. The only thing that was different was the penalty. So let's get the pen on here. So for lasso, we minimize the residual sum of squares plus lambda, and it's a very subtle change. We've got j equals 1 to p. Instead of the sum of squares of the coefficients, we penalize the absolute values of the coefficients. It's also controlling the size of the coefficients, and it seems like absolute value and sum of squares would be rather similar, but the lasso's got a somewhat magical quality. And by penalizing the absolute values, that's actually going to restrict some of the coefficients to be exactly 0. Okay, so we've got to get back to our control here. So let's run that. Again, it fits the whole path. And when we make the plot against the log of lambda, indeed what you see is that initially all the coefficients are 0, and then the first coefficient seems to be a purple. There's a pair of them there. And then the blue one's been 0 up to this point. Then it jumps in. Then this red one jumps in. So you see the coefficients jump in, having been 0 for a length of the path. And at the top of the plot, we actually see, as a function of lambda as well, how many non-zero variables are in the model. So as we saw in the lectures, lasso is doing shrinkage and variable selection. When we fit the lasso using GLIMnet, we didn't tell it alpha because the default for alpha is 1, which gives you the lasso. We plotted the lasso against x var equals lambda. If you look at the help file for the plot, you'll see that there's various choices, and one of them is a really interesting choice, and it's deviance. And what it means is percentage of deviance explained, or percentage of, in case of regression here, sum of squares explained, which is the r squared. So if we make that plot, it's changed the orientation, and at the bottom of here, it says fraction of deviance explained. So that's like the r squared, right? And what you find out here is that a lot of the r squared was explained for quite heavily shrunk coefficients, and towards the end, with a relatively small increase in r squared from between 0.4 and 0.5, coefficients grow very large. And so this may be an indication that at the end of the path there's overfitting. So these different ways of plotting the coefficients give you different information about the coefficients and about the nature of the path. We can use cross-validation again and plot it, and see here's cross-validation for the lasso, and it's telling us that the best model, the minimum cross-validation error is for size 15, and within one standard error we have a model of size about 6, right? And it's somewhat flat in between, and so we may make our choice based on that. There's a coefficient function extractive that works on a cross-validation object, and remember the fit.lasso will have the whole path of coefficients, so it's got roughly 100 coefficient vectors depending on each value, indexed by different values of lambda. But if we extract the coefficient from the CV object, it'll pick the coefficient vector corresponding to the best model, which in this case was the model of size, well, let's see what size, 1, 2, 3, 4, 5. So I guess it's picked the model, it's picked this model over here. So it's within one standard error of the minimum. So it's erring on the more parsimonious side. We know that the cross-validation error is measured with some variance, and so that's the model that's actually chosen. All right. We'll end the session by using our earlier validation training division. So use a validation set to select the lasso model, and that's also easy to do. So we've still got our variable train hanging around, index variable. So we'll fit the path of lasso models using X train and Y train. And you can do a summary of the fit. It actually tells us the summary of a GlimNet fit. For each of the models in the path, it gives you the degrees of freedom, which is the number of non-zero coefficients, the percentage deviance explained, which is like R squared for generalized linear models, but in this case it's squared error loss, so that's just R squared on the squared error loss scale, and the lambda value that corresponded to that fit. And it actually tries to fit 100 values of lambda, but if it reaches a point when nothing much is changing, like you can see nothing much is changing here, it stops, because it's not really making any progress. So as lambda is getting smaller here, the model's really not changing. It's pretty much at the ordinary least squares fit, at the unpenalized model. Okay. So now we can make predictions on our left out data. So that's indexes X by minus train, much like we did before. And if we do dim of predict, there's 83 observations in the validation set. And we've got 89 values of lambda, so there's going to be 89 different columns in this prediction matrix. Here's an interesting little command here. We want to compute our sum of squared errors. Well, y minus train is a vector of length 83. But pred is a matrix 83 by 89. And here we happily say y minus train minus pred. Well, what it does is it recycles this vector 89 times, and it does it column-wise so that it can compute this difference. So the result of this here is a matrix that's 83 by 89, even though we only gave y as a vector, it recycled it, which is it's kind of a trick, but it's a handy trick. We square those errors. We then use apply to compute the means in each column of the squared errors, and we put that in, and then we take the square root. So there's a whole bunch of commands all in one there, and now we can plot that and as a function of lambda, and we see a nice validation curve. It goes down and then climbs up again. This will be overfitting, this is underfitting, and this seems to be the sweet spot over here. And we can extract the best lambda, and yeah, I do this by indexing. There's a component on the GlimNet object called lambda, so this extracts that component. And then I index it by order of RMSE, so that's our root mean square error. Order puts them in ascending order, and so we want the index of the first or the smallest value, and that'll pick up the best lambda. So that's a way of doing that, and we find the best lambda is 19.98. And so now we can look at the coefficients corresponding to that variable, and that'll give us a subset of the coefficients. And the dots correspond to the zeros, so those are the ones that are missing. And so they're not missing, but they're zeros. This is actually printed out in what's known as sparse matrix format. And so, which means only the non-missing values, or only the non-zero values are actually recorded. So there's our coefficient vector. And that's the end of the session. So to summarize, we've, in the last few sessions, we've looked at model selection. We've looked at a variety of different methods: best subset, forward stepwise, ridge regression, lasso. We've used validation sets to select models. We've used CP to select models, and we've also used k-fold cross-validation. We've also seen how to use R Markdown to actually produce a nice recording of everything we've done. And we hit the knit HTML at the top of the page here. And this is for the entire set of sessions on model selection. And you get a really nice summary of everything you've done, all the output, all the plots, nicely formatted, and it makes for a good report. Think about if you're doing a data analysis for a client, this is a really nice way of showing the output. It shows what you did and the results of what you did. And so that's available. It's a web page, and so you can distribute the link to that web page. You can put it in a blog. You can do what you like with it. What we didn't cover was principal component regression and partial least squares. There's a lab in the end of the chapter, but by now you'll have learnt enough tools, you'll be able to go through that lab on your own.